Chapter 10, chemical bonding. So question, just to refresh our memories from last week, is elements form compounds because they want blank. So A, to get 8 valence electrons, B, noble gas configuration, C, N, S2, NP6, meaning the N's meaning a certain energy level, or D, all the above. What do you guys think? And yes, all the above is the correct answer. Good, because those are all redundant, the same thing. I mean, some of these elements, like hydrogen, don't like to have 8 valence electrons. They actually like to have 2. So does helium, and boron, for example, likes to have 6. Some elements are okay with more, but in general, 8 is the golden rule, the octet rule, which we'll learn more about today. And that's characterized by noble gas configuration and NS2, NP6, depending on what that energy level is. So the type of bonds we're going to be covering, there's really the main 2 are ionic and covalent, the ones we've talked about already in this class extensively, and not really talking about metal to metal metallic bonding much. And that's really just metal bonding is you have pooled electrons that are constantly transferred all around the elements, around the metals, because you know metals, they don't want to have electrons, they tend to get rid of them. So in a metallically bound thing, such as a aluminum foil, which is a bunch of aluminum atoms that have metallic bonds with each other to make them rigid in structure, otherwise they would fall apart. And these bonds are held together by oppositely spinning electrons just in a pool together. So determining number of valence electrons, this should be a review for all of you, but just to recover it, if you have group 1A, 2A, those are what? Remember, 1, 2 valence electrons, 3A is 3, 4, all the way up to 8. Those are the number of valence electrons in the atoms. Now, for the ground state, since we are aware and really, we should be really good at electron configuration, we should be able to know or to figure out the number of valence electrons in a ground state transition metal. So we should figure out the transition metal electron configuration. And then the valence electrons in the electron configuration are the ones that have the highest energy level. So for example, if you have a metal that is, let's say neon, and then it's 3s2, or no, that's not a transition metal. So if you have 4s2, 3d, or this is argon, fine. You have argon 4s2, 3d3. How many valence electrons are there? Anybody want to guess? Or it shouldn't be a guess. It should just be a statement. Answer. How many valence electrons? 4s2, 3d3. Yes. Good, 2. And it's 2 because it's not 5 or 3, it's 2 because 4s2 is the highest energy level. So that's very important. The 3d3, even though it comes after in the configuration, the way we write the configuration, it always goes by the principal energy level, the electrons that are furthest away from the nucleus, and that's the 4s electrons in this case. So that's just to recover those rules. So to go over Lewis structures. Now the Lewis structures represent the most stable configuration of a compound. And we are mainly going to be talking about Lewis structures when it comes to covalent bonding, not ionic bonding. Even though they do use ionic bonding as an example, which we'll see in the next couple slides, but covalent bonding is really where it comes into play because we'll be talking about the different bond angles and double bonds, triple bonds, and all that stuff will come into play. So the octet rule, it's very important for Lewis structures is that we want to ideally, sometimes it can be broken and it's more loose than you think. Maybe in high school chemistry you learned the octet rule is the golden rule for how many electrons each of these metals or non-metals like to have in covalent bonding, but it can be broken. So it's generally most of the non-metals like to have 8 valence electrons around their atoms, and either those electrons can partake in bonds or be lone pairs. And again, several elements violate that rule. So here's an example of just how to write the Lewis symbols. And this is an ionic bond example. So for lithium, if you were just to write lithium, it would be Li with 1 dot, right? Because lithium has 1 valence electron. And if you remove that electron, as it would do in an ionic bond, it becomes Li plus 1. That's very, very basic. So for fluorine, you have 7 valence electrons here. It's in 7A, right? So you draw 7 dots around it. And normally there is 2 dots on each side. There's 4 sides. And if you have 8 valence electrons, you're going to have 2 dots on each side. But since there's 7 for fluorine, you're only going to have 1 dot on each side. Or 2 dots on every side except for 1, which will have 1 dot. But once this fluorine gains the electron that it so desperately wants, it will have 8. And it will look like this. Fluorine with 8, and then the whole thing is in brackets with a -1 charge. So this idea is very powerful when it comes time to understanding why things bond. So a good question that I'm asked a lot, you guys are kind of quiet, but I get it, it's a night class, is why do elements bond to other elements? It's a really good question. And something that I've referred to more when we talked about energy is that, oh, everything in the universe happens because it ends up in a more energetically favorable state. And that's true. But to understand that better, something like lithium, like this lithium fluoride bond, this will naturally occur. It doesn't take any energy to happen. It actually loses energy in doing so. It becomes in a more energetically favorable state when this happens spontaneously. Yeah. So the reason why is because lithium has 1 lone electron. This idea of a lone electron is very reactive. So that's something that's important, and we're going to be using that concept throughout learning Lewis structures, that a lone electron is very reactive and not stable. It's called a radical. Whereas a pair of electrons is pretty stable. You know, they spin in opposite directions. It kind of has some stability to it. So fluorine at its ground state has one of those unpaired electrons, right? It has 7 valence electrons. These 6 are paired. This one is not. So what happens is you have a radical. Now, this radical is reactive. So naturally, it wants to gain another electron, and naturally the lithium wants to lose an electron. That's why they want to lose it and gain it. Not because, oh, they just want to get to 8. No, the reason why they want to get to 8 is to pair all of their electrons, because an unpaired one is really bad. That's why. And it actually makes both elements in a higher energetic state. Whereas when they come together, when the lithium gives to the fluorine, this makes both of them happy at the same time, and both of them at the higher energetic state become a lower energetic state spontaneously, just by being in proximity to one another. And this is true for covalent bonds also, that when their octet rule is satisfied and when their covalent bond is established, they go to a naturally lower energy and energy is released. So bonds are favorable in the environment because of this. So if you were to draw an energy diagram, it would look like this. You have, well, different ways to draw it, but whatever. I'll just talk more about it. Now, they're favorable, so hopefully that makes sense. And also, the distance is important. There is a sweet spot Goldilocks zone distance that these atoms like to take between each other that maximizes their bonding potential or minimizes the energy associated with that bond. So there's a common chart out there. So if you were to draw, like, it would look like this, where this is the distance and this is the energy. So if you have the 2 atoms are really, really close together like this, so distance is very, very short, they're at a high energy. That's too short. They're too close together. They kind of repel, the electrons inside kind of repel each other. Then there's a sweet spot distance where the energy is minimized. This is where they bond. So this is their bonding distance. And we'll talk more about bonding distance later. Bond distance. And then as you get further away from one another, your energy increases and they get more unstable. And that's when you have a really far distance, that's when they're kind of completely separated, and then they're at their own energy level that is pretty high in comparison to their bonded state, because like I said, they have their unpaired electrons, which is not very favorable. So any questions on that concept? That's an important concept that we'll be taking throughout this chapter. No? All right. Cool. All right, so moving forward, and more specifically, that's kind of why they bond, but another good question is why they even come together in the first place. And the answer is, oh, not because of this random motion. It's not random at all. They're actually attracted to one another by the electron clouds being attracted to the protons of the other element. So that's why, and that seems, oh, like no duh, obviously, but nobody really thinks about that. Nobody really teaches that. Is that why are these, we know that when lithium comes near fluorine, they do the exchange and that brings them closer together. But why do they come close together in the first place? And the answer to that is because the electron from lithium is attracted to the protons of fluorine, and vice versa. The electrons of the fluorine are attracted to the protons of lithium also at the same time. Even though each one of them has pluses and minuses and technically they're neutral, there still is partial charges within the atom that attract other atoms. That's how they can get close enough together to transfer that electron and actually make a stronger bond, in this case ionic. So that's the fundamental theories behind that. Okay, so here's another example with two lithiums and making lithium oxide. So you have two transfers of electrons. And also, and this makes an ionic bond. So we know about ionic bonds is that they are non-directional. So they're electrostatic, and covalent bonds are also electrostatic. All that means is they involve electrons. They're electrostatic and they're non-directional. This is key, and this is different than covalent bonds. This is why for ionic bonds, you'll notice that we're never going to talk about shape. We're never going to talk about what arrangement the molecule or the atoms like to take around the central atom. It's non-directional. They're kind of, if you have two basketballs and you force them together, any arrangement you put them in, it'll be exactly the same because they're just there's balls, right? They're spheres. Same thing with ionic bonds. All ionic bonds work that way. So because they're spherical, they attract in all different directions, whatever. And they all have a crystal lattice. So they arrange in their repeating patterns. So different salts like NaCl has its own crystal lattice. And we'll talk about that more in chapter, I think 13, we'll talk about lattice energy. We'll talk about that here a little bit too. But we'll talk about lattice structures, body center cubics, face center cubics, and different types of lattices. So here's an example of one of those lattices where you have all the pluses and minuses. They're arranged in certain patterns, and that pattern is proportional, or that energy in that pattern with each plus and minus charge is proportional to this equation. And on the next slide, we'll actually show the equation. And I guess let's go to that right now. So here's the lattice energy of ionic bonds. Now, I would say these equations will be given, at least one of them would. Yeah. And I think the bottom one is better, and this one will be given. If not, the top one will be given with the constant, and it's the same thing. But if you were to solve this and put in, this is epsilon 0 right here, you would get this. So it's the same thing, I'm just simplifying it for you. And what this means is the lattice energy associated with an ionic bond depends on two things. It depends on, well, who can tell me? I'll tell you Q is charge. So who can tell me the two things that it depends on? And how? Yes, this is physics. It's very physicsy. So what are the two things the bond energy or the lattice energy depends on? Good. And yes, Adi got the other one. So Lewis, good job. Distance, and Adi got charge. Okay, so charge and distance. So you see that for Q1 and Q2, that represents the numerical charges of the ions involved and the absolute values of them too. So keep that in mind as well. If you have a +1 and a -1, it's just going to be 1 times 1. If you have a +1 and a +2 and -2, it'll be 2 times 2. And then the radius is going to be in nanometers, and that's usually maybe within 1, 2 nano. No, well, no, maybe 1 to 10 nanometers. It varies, but it's not going to be too huge. It's not going to be like wavelengths that are hundreds of nanometers. So anyway, now something else you could think is, all right, between these two, we're going to learn in depth about these two factors about bond length versus bond strength. That's what the Q1 and Q2 represent. They represent bond strength. So how strong are these ionic interactions? And since they're in the numerator, you can imagine the energy would be larger with larger numbers. And that's exactly true. Because if you have a +1 and a -1, that's going to be 1, right? If you have a +2 and a -2, what's that going to be? 4, right? So if you increase the charges by 1, you get 4 times the energy, lattice energy between them. So that means, and if you get +3 and -3, you even have larger, you have 9, right? So it goes up in cubes, or not cubes, in squares. So what I'm trying to say is that the bond strength is the main determining factor in the lattice energy, as opposed to distance. So distance, it changes a little bit. It varies based on the sizes of the atoms. If you have larger atoms, the nuclei can't get as close to each other as smaller atoms would. Therefore, since the radius would be larger, the bond energy, the lattice energy, according to this equation, would be smaller. But that smallness, or that value, would be small by a little bit. It wouldn't be 4 times as small. It would just be proportional to the difference in the distance between two smaller atoms versus 2 larger atoms, which generally they only vary maybe at most like 50 or so picometers, the radius is. So they don't vary that much, whereas the charge magnitude varies a lot. It could be 4 times or even 9 times, like we saw before. So the bond strength, most important thing, and the radius does come second, but it's another factor. Any questions on that? No? All right. So here's some examples of this in action. So we're going to be talking about this kind of equation in a bit with the Born-Haber cycle. But before that, let's look at some melting points of ionic compounds, and we'll see why that's the case. So NAF. Well, let's establish something. This whole column, what are their charges? The left column. Well, I mean together, yes, but what's each ion's charge? Good, yeah, they're all +1, -1s. So if you put them in the energy equation, they all line up as the same Q. Q1, Q2 are the same. So we're only changing the bond distance based on their size. Now Na and F, those are small. So Na and F, fluorine is the smallest in the S block, not the S block, the P block. And it's really up in the periodic table. You know where it is, and the sodium's on the other side, on the left side. So they're pretty small. And they're pretty small, which means the energy is going to be maximized in the +1, -1 realm. So if that's the case, it'll have let's say 993 melting point. The more energy you have in the lattice energy, the higher the melting point needs to be, meaning the more energy is required to break those bonds. Then you have NaCl. So you're basically replacing the fluorine with a chlorine. Chlorine is a little bit bigger than fluorine. So the bond distance will increase, so the bond energy will decrease, meaning the melting point will decrease. That's exactly what happens. It goes to 801. Then you have NaBr. Br is bigger than Cl. So the same thing happens. It decreases. So you understand that? Does that make sense? As you increase the bond length, the bond energy decreases. And then if you replace the sodium with a potassium, so we can compare NaCl directly to KCl, you see that potassium is bigger than sodium because it's further down in the periodic table. And this lowers the lattice energy as well. So same thing. And then you can see that trend. So, okay, so that's one column, right? So here's what we can do. Let's compare NAF, which is the most stable or the highest lattice energy +1, -1, to the +2, -2, MgO, right? That is a huge difference in energy, almost 3 times, just by making it 1 charge up. So that's to show you that the magnitude of the charges, whether it's a +2 or -2, that matters more to the lattice energy than the distance does. Because, yeah, I'll say like BaO, right? Barium is pretty far down in the periodic table, and oxygen is bigger than fluorine. So this is a pretty big distance. Meanwhile, the energy is still, it takes 1900 degrees Celsius to break that bond, or to break or to melt them, right? So yeah, for this is just to show you that the charges take precedence. So I think you got the point already. And you can see the plus ones, or the plus twos and the minus ones are kind of in the middle. Okay. So the energy of bond formation. Now, I guess we could just skip to the Born-Haber cycle. So there is a way. We already learned about bond formation energy a little bit when we talked about enthalpy. We talked about Hess's law, products minus reactants, how to calculate the energy of formation in a certain reaction. But there's another way to do it based on lattice energies and bond energies. And that's called the Born-Haber cycle. So basically, this is how the Born-Haber cycle works. And don't go crazy about this. This is not an easy thing to do. But if there's a question on it, there might be some on the homework. But if there's some on the exam, it will only be maybe one question. So don't flip out over it. But it is something that we need to go over, and it is fair game. So if you have a given reaction, such as in this case a metal plus some kind of halogen, that equals the metal halide. And we're trying to figure out the enthalpy of formation, this HF. If we don't have the enthalpies of formation of the products and the reactants, or we don't have the bond energies of the products and the reactants, but we have other information, we can still figure it out. By this other information, I mean the heat of sublimation, the ionization energy, the heat of dissociation, the electron affinity, and also the lattice energy. Or we can figure out lattice energy using this. But I'll explain what the hell I just said. So the idea here is to break down the reaction into exactly what happens, or into exactly the pure states of what happens. Now, I'll just say a statement right now. The easiest way to ionize something is to make it a gas. That's just a thing. So, and the reason why is because it's easier to kick an electron off of a gas than it is a solid or a liquid. Much, much easier. So for this metal solid, which will react with the chlorine or the halogen gas, first you need to sublimate it, turn it into a gas. So this is a stepwise process. First, you turn it into a gas. Then you ionize that gas. You get the charge. Add those two numbers up, put that into the equation. So that's where you get heat sub plus ionization energy. Plus, do the same thing to the other reactant. Oh, the other reactant, look at that. It's already in a gaseous form. So what we're going to do is take that and we're going to split it in half, because we want to get just the X by itself. So that's the heat of dissociation. We're going to add that too. Then we're going to do electron affinity, because we're taking the electron that is ionized from the metal, and what we're doing when we make an ionic bond is we're giving it to the non-metal. And that's the electron affinity energy. So that'll be added too. And then all of these, then the only energy required is the energy to make this compound, which is the lattice energy. That's the energy required. So add that energy up. What you get is the heat of formation. So the enthalpy, the energy associated with the entire process of the formation. So it's a very stepwise process. And what we're going to do is we're going to do an example. So we're going to determine the lattice energy of MgCl2 based on this crazy amount of information. So first we have Mg. We can write our equation. Mg solid plus, I think the equation would be 1/2 Cl2 gas yields MgCl2, because we want it to be balanced, but this is the pure way of how to write it. And most of the time they'll give you that. So the first thing we can do is we can do exactly what we did. We can turn this solid into a gas. Do we have an equation with that? Oh, yes, we do. That's equation number 1. So turn it into a gas. We can take this and we can add it. So that's going to be plus 147.1. So we used that already. So we can cross it out. Then we need to ionize it. All right. So here's an ionization. Turns Mg gas to Mg plus 1 gas. That's good. But then what do we know about Mg? Naturally, it's in group 2A. So it has a 2+ charge. So it goes from Mg plus 1 to Mg plus 2. We need to add both of those. So those are going to be plus 738 plus 1450. Now these are done. Next, now we're done with that. We're done with magnesium. Next would be the 1/2 Cl2. So what do we have? 1/2 Cl2 equals Cl. Dissociation. Good. So we add this one. That's going to be 121.3. Good. So now we take this Cl and we're going to ionize it, which is right here. Or sorry, electron affinity. We're going to take the electron affinity of it. But now, since we have 2 Cls, I mean, so we're going to do that twice technically. Since we're doing 1/2 Cl equals 1/2 Cl2 is Cl, we're going to have to do that twice because there's 2 Cl, even though it's half. So, okay, let me explain. So the equation tells you that 1/2 of a mole of Cl2 is equal to Cl. But what about the other half? Since we have a Cl2, the other half is also that. So we need to make 2 times this process with the Cls because we have Cl2. Each one needs to be electron affinity. And another reason why that is because Mg is 2+. So we need 2 Cls to bond to the Mg. That's why we're doing this. So the second one, we just multiply by 2. And then we have the electron affinity, which is right here, which is minus 349. And that's all going to be multiplied by 2. So does that make sense up to that point? If not, ask questions. It's kind of weird, I know, but ask questions. Yes. Yes. So if they were to be that mean to you and give you one of these questions, you will be given all this information. So basically, the way you do it systematically, and it's kind of self-evident once you look at it. Oh, Mg. What do they give me? Oh, Mg equals gas. Yeah, I know I have to add that. Then, oh, +1 and then +2. Okay, I have to add both of those. That's right. Then the tough part would be what I just said with the Cls making it 2 of them, because your total product is going to be MgCl2, not MgCl. So looking at this right now, it's not technically balanced because you have 1/2 Cl2, which is kind of just Cl, but on the right side you have MgCl2. That's why we're multiplying the middle by 2, because it's going to happen twice for Cl. Okay, and then the last thing we're going to add is the lattice energy, which is right here. So this one. Or no, this is the end. This is the formation. So we're being asked for the lattice energy. So the lattice energy will equal the heat of formation minus 641.3. And then basically we would solve this. So we would tally up all this, move it over, subtract it, and then we'd have the lattice energy equals whatever that is. And this is the work for that. And you end up with negative 2,521. Yes. So any questions on that? Yes. Oh. Oh yeah, that's from the heat of formation. Yeah, but this is kind of weird. I don't know. I'm not really a fan of it. It's tough to teach, but that's how you do it. That's what it means. Can I move to the next one? Yeah, so there's our answer. Okay, any other questions? No? All right, switch gears. So here we go about lattice energy in terms of ionic size. We already kind of touched on this, but if you have larger ions, so larger ions means the center of the positive charge is further away from the negative charge. So that makes sense. The radiuses are larger and the nuclei are further apart. So larger ions mean weaker attraction, which means a smaller lattice energy. So very important concepts to have in mind, associations to have, where larger, weaker ions are the weakest lattice energy, the smallest lattice energy. So if you have +1s and -1s that are really far down in the periodic table, those are the weakest. If you have +2s and -2s, or +3s and -3s that are really high up on the periodic table, those are the strongest, based because they have the smallest radius and the largest charge. That will be the largest lattice energy. Sometimes I keep saying this over and over again, and I feel like I'm saying lattice energy. But yeah, so here's some examples. And like I said, the radius between the atoms will only increase by 50 or even 100 picometers, not too much, but the charges will increase by ×4, ×9, or even ×16 if you have a +4 and a -4, which is possible. But you can see how if you increase the size of the metal, lithium going to sodium, going to potassium, going to cesium, the lattice energy becomes weaker. So it becomes, the magnitude of it is important. The magnitude decreases. Because we know when you form what we talked about in the beginning, when you form these compounds, you're releasing energy because they're getting more energetically favorable when they are bound together. So this causes a release in energy, which is why the biggest release in energy means they're the most unstable to begin with, and when they are bound together, they release the most energy. So that's usually when they're higher in charge and smaller, so they can get closer together. Okay, and then we have charge. So the importance of charge, very important, the most important thing, that the larger charge equals the stronger attraction, which is the largest lattice energy. And you can see that comparing a sodium fluoride, which sodium fluoride and calcium oxide have about the same distance between each other, off by a few picometers, but their lattice energies are hugely different. In that calcium oxide is more than 3 times the lattice energy, so it releases more than 3 times the energy when those atoms come together to form an ionic bond. So ionic charge is generally more important, like we said. Okay, so we'll do this. So order the following ionic compounds in terms of increasing magnitude of lattice energy. Oh, Disney answers. Whoops, ignore it. Boom, no answers. Okay, so who can tell me which one's the weakest? Yes, perfect, KBr. Because KBr along with KCl are both of the +1, -1s, so we know they're weaker. But if we put them in order, Br is bigger than Cl. It's further down in the table. So KBr will be the weakest one. And then what follows that? Good. KCl, since it's a little bit smaller, so it'll have a little bit more lattice energy. And then what comes next? Good. Strontium oxide, because strontium is a lot bigger than calcium. So it will be a bit weaker than calcium oxide. And then finally, calcium oxide, which will be the strongest. Good. So that's going from weaker to stronger. Okay, cool. Any questions on that? No? All right. Moving on. All right, so now covalent bonding. We're going to look at that. So we're going to get into Lewis structures now. So we know about this octet rule. We know it's favorable. We know that there are bonding pairs of electrons and non-bonding pairs of electrons, which are called lone pairs. We have non-bonding and bonding, and the lone pairs are the same as non-bonding. Now, for something like CO2, here's technically the correct Lewis structure for CO2, also written like this. Like that. Those are both acceptable. Now, what this means is that each one of these bonds, the line for the bond, so the line, L-I-N-E, the line represents 2 electrons, represents 1 pair of shared electrons. So if you have 2 lines, that represents 4, because it's 2 pairs of shared electrons, and that's a double bond. If you have 3, triple bond, that's 6 electrons total, 3 pairs of sharing electrons. Very strong bond. So in general, single bonds are weaker, double bonds are stronger, and then triple bonds are the strongest, and make the covalent bonded atoms closer together because of the strength. So so that's that. So our goal is to have the octet. Now, Lewis structures, when we're talking about covalent bonds, these are directional. So meaning they have directions, obviously. But let's say water. Water looks like this. This is the conventional way. If you look up water Lewis structure, it always looks like this. That's for a reason. And we'll talk about that reason more in chapter 11. But basically, the electrons, I'll tell you right now, the electrons that are the lone pairs actually push the bonded pairs away and make this bent shape. It makes it bent. That's why we refer to water as being bent, as its molecular geometry. So the direction matters, and the angles between each of the bonded atoms to the central atom, that matters when we're talking about covalent bonds. Okay, so we know that they're weak. What does this say? They have low melting point and boiling point. Yeah, sure. They're found at all three states. Okay, basically it could be anything. Covalent bonds are strong. I mean, so here's a common question. I hear a lot, like people debate whether ionic bonds, what's stronger, ionic or covalent? The strongest covalent bonds are stronger than the strongest ionic. Let's put it that way. There is some overlap. It's not like covalents are up here and ionics are down here. It's kind of like this. There's some overlap. The strongest ionic bonds are definitely stronger than the weakest covalent bonds. But generally, covalent bonds are stronger. But the thing is, their attraction between molecules is pretty weak. So that corresponds to the intermolecular forces. So we're going to learn about that more in chapter 14. Intermolecular forces, meaning the forces that are in between molecules, such as hydrogen bonds, van der Waals bonds, and things like that. So usually for covalently bound molecules, it's pretty weak. They have pretty weak intermolecular forces. Okay, so here's a good thing about rules of Lewis structures. Then we will do some examples, and then, yeah, so we're going to take our break soon, actually. We'll learn this, do some examples, and then you can do some examples on your own, and then we'll go over them after the break. So Lewis structures, here is the way it generally works. Carbon, and these are like almost dead set rules. Carbon, always 4 bonds, never has any lone pairs. If it does, it's messed up and it's bad. So it's always going to look like this, like it's on the bottom, 4 bonds. But they may not be all single bonds. For something like, we'll do an example, HCN. We have these examples written there. Oh, damn, I did that example already. I'm running out of examples. Wait. Okay, so I'll write some random examples. All right, cool. So we'll do those 4 examples as we go along. Nitrogen. Nitrogen likes to have 3 bonds. Sometimes it likes to have 5, but most of the time it likes to have 3. So, and it usually has 1 lone pair. Oxygen likes to have 2 bonds. It can still, and it has 2 lone pairs, so just like it does in water. It could be double bonds, or it could be 1 double bond or 2 single bonds. But sometimes that rule is meant to be broken. Sometimes you can have the octet rule, but 1 bond, but it'll have a charge. Hydrogen and the halogen. So hydrogen, definitely only 1 bond all the time. 2 electrons, 1 bond, hydrogen always. Halogens, most of the time. Sometimes you could force the halogens to be central atoms, and they can break the octet rule pretty easily. But the cases where that happens is not many. Whenever you see halogens that are not the central atom, they will always have 1 bond. So I know I'm just throwing information out here, but I mean, you can rewatch on the video, and also I'm going to be showing you this in examples. I'm going to write another example. Also, so beryllium. Beryllium is a weird one where it only likes to have 2 bonds. So such as beryllium chloride, BeCl2. It just likes to have 2 bonds. And even though you think it might be a metal, it's not. I mean, it is, but it likes to have covalent bonds. Beryllium's weird. Beryllium's honestly weird. It likes to have covalent bonds, but it's technically a metal. So But don't really worry about that too much. Then boron is another exception to the Octet rule. Likes to have 3 bonds with no lone pairs. So it's kind of like hydrogen, not hydrogen, nope, not at all. Kind of like nitrogen, where it sometimes like to have 3 bonds, but this can be broken. Sometimes I've seen it with 4, such as in BF4 minus. That's a thing. Anyway, so the group behavior is generally similar. So by that I mean sulfur. Sulfur, it follows, it's right underneath oxygen. It could also have 2 bonds, but it could also have 6. So it really depends on the scenario. So a lot of these rules you're thinking like, okay, he's just saying like really conflicting things right now. And there's a lot of things. It depends on scenario. And with practice, we're going to do here on the homework, on whatever, on the extra credit, you'll be pretty good at it. So just bear with me. And then phosphorus, another one that's right underneath nitrogen. It likes to have 3 bonds most of the time, sometimes 5, but most of the time 3. Okay, any questions on that before we go over examples? And how? Good question. Is there a pattern that we have to memorize? Not really a pattern. Well, the pattern has to do with the periodic table. I mean, beryllium is 2, boron is 3 valence, carbon's 4 valence, nitrogen is 5 valence, meaning 3 more, or 3 more bonds gets it to 8. Oxygen and sulfur have 6 valence, meaning 2 more gets it to 8, so 2 bonds. And then fluorine and the halogens, it's 1 bond because they're halogens and need 1 more. So it's kind of a pattern. Okay, so let's do some Lewis structures. Here's what I'll do. I'm going to, nope. So I didn't delete it. I just cut it. So I'll put it back later. Okay, so we'll do HCN. Now, things about central atoms. It's an important thing to know when you're drawing these things, which atom comes in the middle. And the answer is one of 2 things, or one of 3 things. Always carbon, never hydrogen, and also if it has neither of those things, whichever one has the least amount. Or if they all have the same amount, it's in order, generally. So HCN kind of follows all those rules at the same time. It's in order, carbon's in the middle, and it's never hydrogen. So the way you would draw it is HCN, like that. Now the bonding, the way the bond works is the first thing you do is calculate how many valence electrons total. That's always a good first step because that's how many dots you have to account for. So how many valence electrons are in HCN? Anybody want to give me the answer? Ding, 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 we have an answer. 14. No. 9. Yes, that sounds better. Wait, no. Carbon has 4. Hydrogen has 1, so that's 5. Nitrogen has 5 also, so that's 10. Yeah? Okay, 10. Close. All right, so now what we can do is draw, there's different ways to approach it, but one, for simple ones, you can draw the dots that correspond to each of the elements. So now that you have 10, we want to draw those 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the reason why I drew it in that arrangement is because that's how many valence electrons each of the atoms have. Hydrogen has 1, carbon has 4, nitrogen has 5. Okay, so now bonding. We know all the time, hydrogen likes 1 bond. Boom. So then if you know all of these rules, it gets really easy. You're like, all right, carbon. Carbon needs 4 bonds. It has 1, so it needs 3 more. Nitrogen needs 3. Ding, ding, ding. Triple bond. 1, 2, 3. Then you can clean it up and make it look like this. And you have 1 lone pair on nitrogen. Okay, so that's a relatively simple example, but are there any questions? No? All right. Next, SF6. What's in the middle? Good, S. And the question, how do you know? Oh, it makes sense because there's the least amount of them. And all of the Fs really all these cases where it's one element and then a bunch more of the other one, they're all going to be around it, even if it somewhat breaks the octet rule. So there's 6. Now, valence electrons. How many valence electrons with SF6? Sulfur has how many? Same amount as oxygen. Sulfur has no. How many is oxygen? So sulfur is right underneath oxygen. How many does oxygen have? You guys should be snappy at this by now. 6, good. So 6 electrons for sulfur. And then for fluorine, how many? Halogens, right? What group are they? 7, good. 7A, so 7, right? So you have 6 times 7. Since there's 6 fluorines, 6 times 7, so that's going to be 35 plus 6 is 42. So we need 42 dots. It's a lot. But we can draw all those in. Okay, so we're going to draw, well, can we just pretend that the 7 or the 7 dots are around the fluorines? We'll put the 7th dot. And the sulfur has 1, 2, 3, 4, 5, 6. Okay. So what do you think's going to happen? What do we know about halogens? They really only want to take one bond. So what do you think's going to happen? We have an answer. Oh, isn't the answer 48? Maybe. Wait. What's 6 times 7? That's not, oh, it's 42. Plus, oh, wow, I'm stupid. There we go. Well, come on, why did nobody correct me sooner? Thanks, Twain. Yeah, thanks a lot. Yeah, okay. On that note, I'm done. No, I'm kidding. That was my stupid moment for the day. Okay, so back to the question is, oh, Adi, it's okay. No, you could, don't be afraid to correct me. Like on simple stuff like that, like I'm going to be wrong on that. The chemistry, I'm more prone not to be wrong, but the math, you never know. But anyway, or less prone to be wrong. Whatever. So what do you think is going to happen here with the bonding? Any ideas? Just throw it out there. And you're probably right. Whatever you're thinking, you're probably right. Exactly. So it's going to be all single bonds of the fluorines to the sulfur. And, oh, professor, that violates the octet rule. Who cares? You got to do it, because if you do it any different way, it really violates the octet rule. So any other way you want to think about it, you would have multiple bonds to fluorine, which is not good. So you're going to have a single bond of each of the fluorines to the sulfur. So the fluorines are going to be happy, and the sulfur, right, I just draw too many. I think oh, this should be connected to this one. Yeah, so like that. So you should have no lone pairs or no lone electrons around the sulfur, and you should have, every fluorine should look like this, have 3 lone pairs around it, and then the 7th one will be bonded to the sulfur. So that's what it should look like. And the reason why, again, the reason why this works is because neither fluorine or sulfur are left with a lone electron, and also fluorine satisfies its octet rule. Sulfur goes above the octet rule because it ends up having 12 electrons, but that's okay, because we'll talk about why that's okay when we get to formal charges. But basically, we want to minimize the formal charges in a covalent bond to make it stable. But if you don't, whatever that means, we'll figure that out soon. But basically, because the fluorines like to have one bond. Okay. Any questions on that? Okay. Next one, NO3 minus. So what's in the middle? N. Good. There's less of them. The oxygens are around. Now we have a minus charge. Okay, so that factors in when we figure out the number of electrons. So we have a comment. Should there be 32 electrons? Probably. So nitrogen is 5. Oxygen is 6, so that's 18. 18 plus 5 is 23. Minus charge, so that's going to be 24. So yes, it's okay. So I'm not the only one that's losing their sense of math today. That's good to hear. So 24 electrons. Now the oxygens are going to have 6. So 1, 2, 3, 4, 5, 6. They're always going to have 6 because they're. And here's another thing. Here's another little tip. If you have more electronegative atoms, when you're making these Lewis structures, keep them in the priority of being happy. If you have electronegative atoms that are not happy or not stable, generally that's not good for the structure. But again, it depends on the situation. That's just a general tip. And then nitrogen, so we have 18 here, then nitrogen will have the remaining 6. Even though nitrogen normally has 5, it'll have 6 in this case. So the way this works is you're going to have, and it's weird. So naturally, okay, so let's hear some ideas. Let's hear some ideas. What do you think? Perfect. That's exactly right. Yeah. So basically what happens is you have 2 double bonds between nitrogen and oxygens. Then you have a single bond, and then the remaining oxygen or the remaining electron moves over to the oxygen. Or you could think about it as it didn't go to the nitrogen in the first place. There's different ways to think about it, and you could just put it over here. So reasons. Let's talk about. Let's backtrack. We'll put it here for now. Okay. So again, this gets into formal charges, which we'll talk about later. To minimize the formal charges, this is the best arrangement. But reasons. These 2 oxygens are happy. The ones with double bonds, they're good because oxygen likes to partake in 2 bonds. That's great. Nitrogen. If we put another bond here, let's say we did this, because that's a logical choice to begin with. What will happen is this nitrogen will have 6 bonds. Its formal charge will be really out of whack. But again, we'll get to that. So it's not a favorable situation. If we just did the single bond and that's it, we have another unfavorable situation. We have a single unpaired electron here and a single unpaired electron with the oxygen. We know that's not happy. That's not good. We don't want radicals. We don't want single electrons. So this electron will have to be paired with this oxygen. So if you look at it in this case, every oxygen obeys the octet rule. This one has 2, 3, 4, 5, 6. In the bond will be 7, 8. And then these 2 are okay. The nitrogen is a little bit above. This has 10 electrons instead of 8. And this electron will be minus 1 charge. So this is the best possible arrangement. Now this is a more advanced one, I'll admit, but because there's a lot of things to think about. But again, when we get to formal charges, it'll make more sense.
Can you just give a basic rundown about all that again, just really quick? Because
yeah, sure.
I'm trying to wrap my head around it.
Okay, so the idea is you want to make all of the electronegative atoms happy. So oxygen likes to have 2 bonds. So that's why we have 2 out of the 3 oxygens with 2 bonds. The third oxygen can't have 2 bonds. Why? Because if we have the second bond with the nitrogen, then the nitrogen will have 10 electrons. And once we get into, or we'll have 6 bonds. Once we get into Formal charge, we'll see that's very unfavorable. The formal charge would be pretty big, which is not good. But even if we didn't know about that, we want, so if we have generally an oxygen with one bond, so that's a good thing to know. Oxygen with one bond equals -1 charge. So we know that NO3 minus is a -1 charge. So if we need, if you see a single bonded oxygen, that means that oxygen is -1 charge. So that's another way you could figure it out. And also, this electron needs to be on the oxygen because if it's by itself, it can't be by itself. It has to be paired with another electron. So those are general concepts that apply to this, and there's a bunch of them. So I understand if that's difficult, but we'll do more examples. Okay, so let's do one more. So we can, this one we can save for later. So SO3. So what's going to be in the middle? Good. So oxygens are on the outside. Electrons. Let's just do, they're all the same number, right? Sulfur has 6, oxygen has 6. So 4 times 6 is 24. No charges, so that's good. So now we can write 6 on each. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So what's going to happen? There's no charges, right? So the oxygens, what are they going to, what's the best for them? Good, Adi. All double bonds to all 3. But you said that in a questioningly manner. So I will go through why. So first, the first thing to do when you're troubleshooting this, and it's kind of like a puzzle. So it should be, you guys should be having a good time. Maybe not now, but when you're doing this later, you should have a good time. First, draw a single bond to everything. And then just look at the situation. Be like, is this good? And the answer is no, for multiple reasons. One reason, sulfur has an unpaired electron. All the oxygens have an unpaired electron. So that's not good. It'd be like, what about if I move those unpaired electrons to all the oxygens? That means they make them paired. But what does that do? That makes all the oxygens have a -1 charge because they'll only have one bond. You're giving them an extra electron from the sulfur. That means it will get minus. It will become minus. But our structure, SO3, doesn't have a charge. So that can't be a case either. Then your only logical conclusion is, all right, what if we make double bonds with that extra electron on the sulfur, the extra 3, going to each oxygen? That's the best case scenario because all of your oxygens, octet rules, will be satisfied with 2 bonds. So that means they're all good. And then your sulfur will have more, but sulfur likes to have 6 bonds sometimes. That's okay. And it will have its 6 valence electrons. No electrons will be gained or lost because there's no charge. And that's basically how you do it. So any questions on that one? And out of the ones we've done so far, we've only done one that's straightforward, where it's HCN. So keep that in mind as well. The other ones either violate or you have to think a little bit. Okay, so now what we're going to do is we're going to take a little break, and we're going to do these 4. Well, 3. Well, I'll do. I'll make this XeF2 minus. That's a tough one. So put another one in there. Let's do COF2, cough. Sure, COF2. All right, so do those 5. We'll take a 10-minute break, and then we'll come back at 7:22. N is in the middle, 3 single bonds to H. Oh, what about, so there's something else missing from that explanation. So Adi says NH3 is, N, okay, you got it. Yep, lone pair. All right, so N in the middle, 3 single bonds to the hydrogen and a lone pair. It's exactly right. So good, because hydrogen likes 1 bond, we know that. And then the nitrogen has 5 valence electrons. So Only 3 out of those 5 are going to have bonds. The other 2 are going to be remaining. So as unbonded, but they are going to be paired. Nick, no, I don't think you got them wrong. So we'll see. Hopefully you didn't, but if you did, we'll learn. So Adi, so CH4, oh, you're on a roll. Yep. Methane, that's 4 single bonds to the carbon. So it's just like NH3, but we have 4. And we know carbon likes to partake in 4 bonds with no lone pairs. That's one of these rules you don't really break. Carbon always likes to have 4 bonds, no lone pairs. What about H2CO? Perfect. Could have said it better myself. And Adi, you are correct as well. So what Yasmin said was you have the C in the middle. You have the oxygen out here. You have the hydrogens. So you have a double bond to the oxygens, 2 lone pairs on the oxygen like you do for a normal happy oxygen. Then you have the 2 single bonds to the carbon with no lone pairs on the carbon. So that's perfect. You have your 4 bonds, your hydrogens, and your carbons and oxygens are satisfied. Now, before we get to XeF2 minus, which this one we'll do together to save time, what about COF2? Good. Perfect. So the same idea, just with fluorines, honestly. So you're going to have your 6 electrons, 3 lone pairs around the fluorines. You have your fluorine single bonded to the carbon, which is double bonded to the oxygen that has 2 lone pairs. So perfect, good. Now, something like this, which is the weird exceptions, like we went over in the previous slide, XeF2 minus. So what's going to be in the middle? What do you think? Good, Xe, because there's less of them and it makes sense. Then you're going to have fluorines on the outside. Now, in terms of electrons, you know there's going to be 1 more electron since it's minus charge. So xenon has how many valence? How many valence electrons do they have? It's noble gas, right? How many is that? 8. Yeah, perfect. 8. Fluorine is 7. So there's 2 of them, so that's 14. And then you're going to add another one. All right, wait. I think this should be minus 2. Yeah, I think I drew this wrong. It should be minus 2. So then you're going to add 2 more. That's going to be, because it should be even. Because then it's going to be, what was that, 24. 24. If that's the case, that's what I was afraid. I was afraid I drew it wrong. That's why I didn't want you guys to answer it. So we have 8 here. Then we have our fluorines. And basically what's going to happen is you just force single bonds. That's basically it. You're going to have your 8 like that. Yeah, wait, is that 20? How many is this? That's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh, I don't think this has a charge. Whoops, my bad. Well, it could. It could have a minus 2 charge, but I think the best way to write it is just XeF2, not minus. So yeah, I drew it wrong. I'm sorry. But basically, what's going to happen is what I was trying to get across is that if you have something weird like this that clearly violates the octet rule, I mean, you're going to have 3 lone pairs. So that's going to be there, and then you're going to have that's 6, and then you're going to have 8 and 10. And then you have the fluorines on the outside. The important thing is that you satisfy the most electronegative atoms, which in this case is the fluorine. So you want to satisfy those. And everything else, you kind of just force it. You kind of force single bonds with the fluorines or with halogens. That's the way you do it. Because of what we're going to talk about next, which is formal charge. So the formal charge, what it is a way to quantify how far off the elements in a covalent bond are from being happy or being in their formally stable state. That's formal charge. So a stable molecule is going to have no formal charge. The larger the magnitude of the formal charge, the worse it is. So you want to minimize these formal charges. That is the goal of every Lewis structure. And in Lewis structures that don't violate the Octet rule, you'll see that the formal charge is 0 all around. And you can do this on your own when you practice. But basically, the way you calculate this formal charge is this equation right here. And this is the hard way of explaining it, but there's an easier way. So the formal charge equals the valence electrons of the element. So let's say it's carbon, it would be 4. For hydrogen, it would be 1. For sulfur, it would be 6. Minus the non-bonding electrons. So the ones that are electron pair, lone pairs, each one of those singular electrons. So for example, we'll do a simple one. We'll do water. Right? So water has 2 lone pairs. So valence electrons for oxygen is going to be 6. The non-bonding electrons will be 4 because there's 2 lone pairs. Each one of them has 2, just 4 dots. Minus 1/2 times the bonding electrons. In other words, the number of bonds. And number of bonds are 2. So it's going to be 2. This equals 0. So it's going to be, let's rewrite this. We can have Fc equals valence minus non-bonding minus bonds. So that's another way you can think about it. So the idea is when you write these Lewis structures, you want to write them in a way that satisfies the formal charge being 0 or as close to 0 as possible. When you violate sometimes, or when you violate the Octet rule, sometimes you have to be not 0. It could be -1, could be -2, but if the net formal charge is 0, that's also good. All right, so let's take a look at some examples. Now for carbon, for CO2, this one that works out perfectly, everything satisfies the Octet rule, and you see that all the formal charges are 0, but we can calculate that. So we'll do carbon. So carbon has the valence electrons 4 minus the lone pair electrons, the non-bonding, which is 0, minus the number of bonds. 1, 2, 3, 4. 4 minus 0 minus 4 equals 0. Carbon's good. Oxygen, you have 6 minus the lone pair electrons, that's 4, minus the bonds, which is 2, equals 0. So that's all good. Let's take a look at this one. Selenium with oxygen and difluoride. I don't even know what that's called. But regardless, this is the correct Lewis structure for it. The fluorines are satisfied. We'll look at that. Fluorine has 7 minus the lone pairs, which is 6, minus the 1 bond, which is 1. So that's 0. Well, both fluorines are happy. Oxygen is not happy here. So oxygen is 6 minus the lone pairs, which is 6, minus the bond, which is 1, equals -1. Then selenium. Selenium is below nitrogen, I believe, below phosphorus. So it'll be 5. No. Below silicon, so it's 4 minus. No, wait, it's below, oh, sorry, it's below oxygen. It's below sulfur, right? For selenium. Yeah, below sulfur? Yeah, okay. Below sulfur. So even I need a periodic table. So selenium is going to be 6 minus the non-bonding, which is these 2, minus the bonds, which is 3. So 6 minus 2 minus 3 is +1. So if you look at this, this is the best way to write this Lewis structure, because the net formal charge is 0. What if you did it this way? And this is another acceptable, well, actually, wait, there's really not another way to do it. So here's what you can be thinking. If you're going through this problem, I want to get into your mind of like, what, if you're first learning this, what would you be thinking? A good thought would be satisfying the oxygen. So let's see what happens if you did that. You would have the fluorine's good, the selenium, you'd have double bond to the oxygen to satisfy it. What would happen is, let's start from scratch. you have 6 electrons here. 1, 2, 3, 4, 5, 6. This is good. This is good. Double bond here. So you'd have that. So you'd have one lone pair. So that kind of works. And then you have 1, 2, 1, 2, and so that would kind of work. Wait, do they have too many electrons here? Wait, so how many? Hold on, I think they made a mistake here. So let's see. Selenium's would be 6. Let's be 6. That's 12 plus 14 is going to be 26. So it should be 26. So that's going to be 12, 13, 14, 16, 18, 20, 26. All right, that makes sense. Okay. So you would end up with this if you double bond it. Wait, what? They added electron? Yeah. Wait. Yeah, they added an electron. Yeah, this might be, it should be, I think they made a mistake here. It should be minus. But regardless, let's say you did it without a charge, whatever. Let's say you just did it. So what would happen is the formal charge of the selenium would be pretty big. So let's take a look at it. So selenium would be, actually this would work, right? Yeah, selenium, this would be 6 minus 2 minus 4, which would be 0. So this has to be a minus 1 because the oxygen is minus 1. So I think they really messed up here. Yeah, because this is how it's, this makes it all happy. Ta-da. All right, that's weird. Sorry about that. Let's look at the next one. NO2 minus. So NO2 minus, nitrogen's in the middle. To make this happy, the nitrogen will have 3 bonds, right? If you have 4 bonds, that's not good. The formal charge of nitrogen will get too big. Let's take a look at that. So in this case, the formal charge of this oxygen is minus 1. The formal charge of this oxygen is 0. And the nitrogen will do 5 minus the non-bonding, which is 2, minus the bonding, which is 3, or the bonds, which is 3, which is 0. What if you satisfied this? If you did that, you would remove an electron from here and remove an electron from here. What that would do is would make this electron go over here. But it would remove the formal charge off the oxygen there. So what would happen is you would have 5 minus 2 minus 4, which would be -1 on the nitrogen. I guess that would be technically be acceptable too, but we know, I mean, we know from just experience that our charges should be on the oxygen. So if you play around with it enough, you might get 1 or 2 answers that might make sense, but usually our charges are on the most electronegative atoms. That's just a thing. So oxygens, fluorines, things like that. Okay, next one, P2H4, they're all 0. And let's calculate the one for phosphorus. So 5 minus the non-bonding, which is 2, minus the bonds, which is 3, equals 0. So that's good. Okay, so that's how you do formal charge. Is there any questions on how you calculate the formal charge and what our goal is with calculating formal charge? We want to minimize things. Minimize the formal charge. No? All right. Okay, so the sum of the formal charges is the overall charge of the ion. That's another thing that's important. So they correspond. Like this is basically why, remember all those polyatomic ions, like CO3 2 minus, PO4 3 minus. For practice, try to draw the Lewis structures for these without looking them up. And the formal charges add up to -3, -2, +2, whatever the polyatomic ion might be. This is why that's the case, because of formal charges. So the best structure is the one that keeps the formal charges of the atom small. So the lowest formal charge total. And more specifically, the smallest formal charge in each individual atom. So let's say if the charge of the entire molecule is 0, but you have a formal charge, one of them is +4, the other ones are -1, -1, -1, and -1. even though they all equal 0, there's something wrong there. That's not good. Because something with a formal charge of +4, that's crazy. The formal charges, the maximum and minimum you should see is maybe -1, +1, maybe -2, but definitely no more than that. So it should be a very small absolute number for formal charges. Okay, so then we can get into resonance, but resonance you can go crazy detail if you get into orgo, but basically resonance means that the molecule is identical. It's exactly the same, but the bond moves. So that can happen. If you have a secondary bond, a double bond, the bond electrons could actually move to the next bonded pair if they're similar in behavior, meaning like if you have this double bonded oxygen compared to a single bonded oxygen, the double bonded oxygen electrons could move, and then that can move to there, and you can have 3 different resonance structures. So this is possible. Why is this important? Because of orgo, because of sometimes different resonance structures are not identical. Sometimes they're if more complex molecules are not identical and they behave differently. So that's one case. Yeah. So rules of resonance structures. Let's see if there's anything here that's important. I doubt it. So resonance structures are the same connectivity. We know that. They have the same number of electrons. They're identical, but the electrons are moving. The formal charges are moving. So the formal charges must be the same for the resonance structures, obviously. It's the same molecule. Better structures have fewer formal charges. Better structures have formal charges on more electronegative atoms. We went over that rule already. That's important. So if you were to have a formal charge, you would have, that's why the oxygen always takes the charge, because it's more electronegative. And it's more likely, you don't see an oxygen with a +1, you always see it with a -1. The reason why is because oxygen is more likely to take an electron and to give one. So that's why you see that. So here's examples of the Lewis structures, the Lewis structures showing the resonance structures. So you take this double bond and you move it to over here, for example, it just changes which atoms are charged. So yeah, that's one way this is one way you can draw NO3 2-, but the best way is to do 2 double bonds. Yeah, this is actually not a good way at all, because the formal charge of this one is going to be of the nitrogens +1. You have too many formal charges there. You can make this all just -1 with just one oxygen being -1. Better. Okay. So I know that's a little bit convoluted, but is there any questions on that? Just resonance, you can move the bonds around. Same exact molecule. That's it. No? All right. Okay, next, bond polarity. So we didn't talk about electronegativity in this class, so we will now. Or maybe I hinted on it, but basically, in covalent bonds, you know the electrons are being shared. You can have equal sharing and you can have unequal sharing. The unequal sharing means that the bond is polar. And polarity means you have a big difference, not necessarily a tiny difference, but a bigger difference in the amount of pull that the atoms in the covalent bond have for electrons. So electronegativity is the factor that determines how much these atoms pull in electrons. And this results in a polar bond if you have a difference in these electronegativity numbers bonding together. So a polar bond represents its unsharing electrons, and this ends up with a partial charge. So you get partial negative charge and a partial positive charge. An example of that is water. So water is one of the hallmarks of polar solvents. And in water, the electrons in the covalent bond, we're only talking about the ones that are bonded in this case, are going to be pulled more towards the oxygen like this. This makes the molecule of water polar because there's an unequal distribution of electrons in the molecule. And what this does is it makes a partial negative charge by the oxygen and a partial positive charge by the hydrogens, making the molecule charged, partially charged, positive minus. This is also called a dipole. Just like the North Pole and the South, the Earth is a dipole. It has a positive end and negative end, two poles, which moves our magnetic field around. So, which establishes our magnetic field. So with water, it's the same kind of concept. You have a minus end and a positive end. So in this case, you have two positive ends, but same idea. And the way you determine what's the positive, what's the minus, what's going on, is this concept of electronegativity. And electronegativity is represented by a number for each element. And this number you don't have to memorize. This number is given when it's supposed to be used in an exam or in a question. It'll be given. And also there is a general trend that is very similar to a couple of the trends that we learned about already. So what electronegativity is the measure of pull of an atom in bonding pairs, electrons. It increases across from left to right. It decreases going down. So basically the top right of the periodic table, fluorine, is the most electronegative atom. This doesn't include noble gases. They are not electronegative at all because they don't want to react with anything. When they're in covalent bonds, they don't want to pull in electrons or give away electrons. They're completely happy. They don't want to bond. So we don't consider them to be electronegative. But fluorine is the most electronegative and francium is the least. The larger the difference in electronegativity between the two atoms, the more polar the bond is. So the negative end toward more, the negative, when it's negative, the more electronegative atom is the negative end. That's what this broken English is trying to say. I didn't write that. Anyway, so there is the electronegativity chart. And the trend I will draw, I don't know what I did there, but the trend I will draw is it goes up to the right like that, diagonal. Generally, I mean, there's some transition metals that are wacky, but generally it goes up to the right. And in hydrogen's over here, it's a little bit higher than the other ones on the left because it's a non-metal, but generally it goes to the right. It increases. So, for example, if we were to have a bond between H and F, that is extremely polar because H is 2.1, F is 4.0. The difference in that is 1.9. That is huge in electronegativity difference talk. Something small would be 0.5, 0.6. That would still be considered polar, but weakly polar. Something like 0.4, 0.3, 0.2, that we can consider as kind of non-polar. So this is whole spectrum of differences. Now, here's that example, HF. So HF, very polar. And what it does is you see there's a very big unequal distribution of electrons. The fluorine will kind of pull in all of them because it's very electronegative, giving the fluorine a large partial negative charge, and the hydrogen will have a large partial positive charge. That's a very polar molecule. So here's another representation of the electronegativity scale. It increases going to the top right. Okay, so here's more specifically about these numbers. And again, these numbers you do not need to memorize, but they will be given when you need to use them. So let's look at, before we look at definitions, let's look at the scale. From 0 to 0.4, meaning the difference, not the value. So if you have electronegativity difference of between 0 and 0.4, for example, I'll circle some. The bond between carbon and sulfur is not really polar. Their difference is 0. The bond between silicon and phosphorus, not really polar. The bond between silicon and hydrogen, not really polar. The bond between carbon and hydrogen, it's on the cusp, but it's considered non-polar. So you get the point. Anything that has a difference of 0.4 or less is considered to be non-polar. So if the difference is actually 0, where here's the key thing, even if the number, this is what gets a little bit confusing, even if the numbers are identical, such as phosphorus and hydrogen, they both have 2.1, that is not considered pure covalent because the sizes of them are different. Phosphorus is a lot bigger than hydrogen. So there will be a tiny partial charge distribution towards the phosphorus, but it'll be very, very small. So what I'm going to get at is that this Pure covalent means they're identical atoms. So the only things that can be purely covalent is if you have the same two nonmetals bound to each other, just as H2, F2, O2, N2, etc. So that's what we mean by pure covalent. So I think Hao had a question. Oh, that was a long time ago. What is the 1/2? Was there a 1/2? Oh, this, the formula? Yeah, that's just 1/2 of the number of electrons. So the bonds, basically the bonds. Okay, cool. All right, so nonpolar we know is the difference between 0.1 and 0.4, or if they're different atoms and they're covalently bound but have a very small difference, it's considered nonpolar. Polar is when they have, so here's what I don't like. We should not talk about ionic bonds when we're talking about electronegativity differences. I'll tell you why in a minute. It confuses you. So when you have greater than 0.5, so atoms that are bound together that have a difference in electronegativity of greater than 0.5, it's considered to be polar. So such as if we have oxygen, so polar we would have such as like fluorine and oxygen. Fluorine and really anything else would be a polar bond. So that's that. What they say about ionics, though, they say anything above a difference in 2.0 is considered ionic. Yes, that's true, but I don't like that, and I'll tell you why. Because that confuses the hell out of you. Don't think about electronegativity when we're talking about ionic bonds, because we can characterize ionic bonds with ease compared to covalent, right? Ionics have a metal and a nonmetal. Covalents just have nonmetals. So wherever you see metals and a nonmetal together, that's ionic automatically. You shouldn't have to look at differences in electronegativity to determine how ionic, or not how ionic, determine if it's ionic or not. You can use the difference in electronegativity to determine how ionic it is. So there is an actual level of, I'll use this word, I just made it up, ionicity. That's not a word, I just made it up. But there's a level of this. If you have a huge, huge difference, such as 4.0 in electronegativity, then that's more ionic than something with a 2.5 difference. So there is a range of that. It's a spectrum of ionicity. But generally, do you understand what I'm trying to say? Is that you shouldn't characterize ionic bonds by, oh, there's a difference of 2.5, therefore it's ionic. No, it's a metal and a nonmetal, therefore it's ionic. That's a much better way of classification. The polarity with covalence perfectly makes sense with the electronegativity differences. So does that make sense with what I said about comparing pure covalent, nonpolar, and polar? And all that rant about ionics? Yep. Okay, cool. So here's an example of the polarity. We get it. So what this polarity means is it has a dipole. So we call it a dipole moment, meaning which is kind of from physics, but there is a difference in electronegativity. The larger the difference, the larger the dipole moment, meaning the larger the charge difference. So metallic bonds, honestly, don't worry about this. There's just a sea of electrons. Cool. All right. So the last thing we're going to cover is bond energies. So we talked about bond energies when it comes to ionics. We beat the dead horse when it comes to bond strength versus bond length and all that stuff. But let's talk about covalent bond strength. And really that's only depends on two things. Again, but there's two different things. It represents the number of bonds, meaning the larger the bond energy, or sorry, the larger number of bonds, the larger the bond energy. Triple bonds are bigger than double bonds, which are bigger than single bonds in terms of energy. That brings them closer together. And again, if they're closer together, that also determines the bond energy. Also, shorter ones are stronger, very similar to ionic. So if you're comparing single bonds such as Br and F, versus Br and Cl, Br and F will be stronger because fluorine is stronger, or smaller than chlorine. So it'll be stronger, and then the chlorine will be stronger than the Br because bromine is a lot bigger than chlorine. So it follows the same kind of trend, and we know that triple bonds are stronger than double, which is stronger than single. Okay, so we kind of got that already, same thing. So bond length, yeah, same, whatever, same concept. Now, bond energies. We can calculate by this equation the bond energies and the enthalpy of the reaction of any equation based on the bond energies. We can break down a reaction into bonds. James Bond. No, just regular bonds. My name is Bond, covalent bond. You know I had to make that joke eventually. So here's the equation. And it's a little bit different than what we talked about when we're talking about enthalpy of formation, where we talked about products minus reactants. In essence, this is doing the same thing, but we're taking the energy of the bonds broken minus the energy of the bonds formed. But that's not products minus reactants. It's actually reactants minus products. But it's kind of flipped because making the bonds is exothermic. Meanwhile, bond breaking is endothermic. You have to put in energy to break the bond. So it kind of reverses. It kind of all works out if you compare the two numbers and how you got them. But let's just focus on one thing at a time. If we use the bond energies, it's the bonds broken minus bonds formed. So just keep that in mind. And that equation, I'm not sure if it'll be given. So just definitely, you might want to take a note of that. So and this means this sigma, this means the sum of the bonds formed. Or sorry, broken minus sum of the bonds formed. And here is a bond energy list. Now we can solve the bond or the energy of formation of any reaction using this. So let's do this one. We'll do this example. And then we'll do another example. Yeah, we'll do this example, but then there's some other things I'm going to mention in it. But anyway, okay, so what we do is, and the chances are the reactions won't be given like this. They'll be given in just like H2 plus O2 equals H2O2. And it's your job to first draw the Lewis structure, and second, identify which bonds are in there, and then calculate the bond energy from that. Okay, so bonds broken minus bonds formed. Bonds broken, HH. And assume all the bonds will be broken. We have HH. So what's HH? HH is 436. So 436 plus O2. So it's O double bond O. So we have to go all the way over here, and we get 498. So that's going to be bonds broken minus bonds formed. We have 3 bonds formed. We have 2 OH bonds. This is 1. This is 2. OHs, you have 464. So 2 times 464 plus the OO single bond. This kind of looks like glasses. Draw a nose, smiley face. That. Okay. So we have an OO, and that's going to be 142 plus 142. So does that make sense on how I got that? So bonds broken minus bonds formed. No? Okay. All right. So then we do the math for that, and we get this. Negative 136. That's how much energy is released when you form those bonds, because the bonds are favorable. So we're releasing energy from the initial starting material. Okay, so there's other things you can do. So let's say we had another equation. We'll do it real quick. 2H2O plus, oh, we could do let's do a combustion. So it's combustion of methane. CH4 plus O2 yields H2O plus CO2. So reaction here, we'd have 2 there, and then we'd have 2 here. Okay. So let's figure out the enthalpy of formation of the combustion of methane. Very simple reaction. We've seen it before. Okay, so bonds broken. So I'll write it. I'll try to section off. Bonds, not broken, broken. Okay, so the first thing, we have CH4. We know from the Lewis structure of CH4 that it's 4 CH bonds. So if you were doing this problem, take the time, write down the Lewis structures, and you see that it's 4 times the CH4 bond. So 4 times the, or not the CH4 bond, the CH bond. Then the next thing would be 2 times the O2 bond, because you have this coefficient 2. So 2 times the O2 bond, which the O2 bond is a double bond. So that's going to be the bonds broken. So the reason why I want to do another example is because I wanted to show coefficients. So you have to do it every single bond that is in the reactants, add them up, minus every single bond in the products after it's balanced. That is the whole picture. That's going to be minus the bonds formed, 2 times an H2O. Now, if you look at H2O, each H2O is an H single bonded to an oxygen. But there's 2 of them now. So, or sorry, each H2O is 2 of those bonds, but there's 2 of these molecules in the equation. So that means 4. There's going to be 4 OH bonds. Does that make sense? Yeah, okay. Then we have CO2. So CO2 looks like this. You have 2 double bonds of CO. And that would be over there, but minus and then 2 CO double bonds like that. So you would take the numbers, put them into here, minus the numbers, put them into here. And this would be bonds. Okay. Any questions on that?